we found that the friction is directly proportional to the normal force. In the special case where you're pulling it along a level surface with a parallel force, we found that that normal force is equal to the weight, and the friction in that case is proportional to the weight. We've also found that the friction is independent of the surface areas, the area that's in contact. And now something that is very obvious, it does depend upon the surfaces that are in contact. For example, a tire on a dry asphalt road has a different friction when the tire is on a wet asphalt road. You know that there's more friction depending upon the surfaces in contact. But watch this. Let's measure what the friction is when cork is pulled on a carpet. I have cork covering the bottom of a block, and I'm going to take that and pull it across the carpet, and you see the friction is about 1.8 newtons. Cork on carpet, about 1.8 newtons. Now let's take that same cork and put it on very smooth wood. And what we see is this. We pull it, we measure the friction, and it's about very close to 1.1. It's in and out around 1.1 newtons. So the friction is different. Now I will take a wood bottom and put that on carpet, and let's see what the friction is of the wood on the carpet. And as we pull it, we notice this time the friction is about 0.8. Different friction for each different surface in contact. There's a constant that represents these two surfaces that are in contact, and it's called the coefficient of friction. Every two surfaces in contact have a different coefficient of friction, and they're represented by the Greek letter mu. You can look these up in books, and people have tested, thousands of materials, and you can find the different coefficients of friction for the various materials that are in contact. The formula for friction is equal to mu, which is a constant reflecting the nature of the two surfaces in contact. It's called the coefficient of friction. This is multiplied by the normal force.